Recording. Cool. So today is going to be sort of a half and half, sort of mix between working through introductions to neural networks, and then also our sort of job search, Ask Me Anything section with all three of the global instructors, starting at 10:30 Central, 11:30 Eastern. That's a really exciting thing. We're really happy to talk about our experiences and sort of give you that look forward at what you'll be going through in the next few weeks. So please definitely think through some of those questions that you might have about the job search, what employers are looking for, how to best sort of situate yourself in that market. In the DSI Plus EC chat room, I've gone ahead and I've pinned that questions thread that Adam put up there. So go ahead and take a look at that. Oh, you can't hear me. Okay. Okay, is it just Chicago that can't hear me, or is it everybody else? Okay, I think New York can hear me. At least I'm going to assume that's what the thumbs up mean. Okay, so Boston can hear me. Okay, so Chicago, what's going on? Okay, cool. Let's vamp for a second. Let's get Chicago settled. All right, one second, everyone. We're just going to sort of do some really quick tech stuff, and we'll get this working. All right, somebody's typing. This is a good sign or bad sign. Could be both. Huh. If I could, Frank says I should just speak louder. And sadly, I'm more than a few blocks away from the Chicago campus. Otherwise, I just shout and they'd be able to hear me. Let's see. Don't know if there's anything I can do from this end. Cool. Let's So while they're taking care of that sort of stuff, I'll just kind of put out a couple of different things that are out there. So you all know the current notebook that we're sort of working out of, which is, let me go ahead and share that screen. So obviously we have our sort of neural networks repo over here. You should have been able to go ahead and clone and pull that down. Definitely, if you're the type of student who is working out of the solution notebooks, don't work out of the solution notebooks this time around. Our checks for understanding are really conceptual, and sort of seeing that answer before you grapple with it is just going to kind of rob you of the chance to learn from that. So if you're in that solutions notebook, throw it out to the side. Don't look at it. Wait until we're through the lecture, then go back and review if that's something you'd like to do. The other thing that we'll sort of be working out of is this playground.tensorflow.org website, and that's going to be sort of a and so this is basically a sort of fake neural network that sort of sits in your browser. It's run by TensorFlow, which is a Google-made neural networks library, and so it lets you play with certain parts of that neural network. And so we're going to use this as our kind of way to try out the different things that we're learning without sort of having to go through in Python and make it ourselves. So kind of how we did that sort of SQL stuff in our way back when we did SQL, we did it in the web browser. This is sort of that same experience. So anyway, that's playground.tensorflow.org. But anyway, today we're going to sort of talk about what the difference between a single layer and a multi-layer perceptron are. So neural networks have a lot of different shapes and types. These are the most simple or the most like sort of introductory. There's a whole host of different terms that we're going to talk about. So epoch, learning rate, activation function, hidden layer, yada, yada, yada. Lots of jargon. We'll talk about how networks are fit. So that's through a process called forward and backward propagation. And then we'll sort of talk about what overfitting is and how we avoid it within neural networks. Because just like any other sort of structured machine learning technique, we are going to create places that might be more or less overfit in terms of our sort of networks. So anyway, I'm going to hop over into my notebook. Let me go ahead and zoom that up a little bit so it's a little easier to read. And we'll kind of get started. As you can tell over here from lines 1 through 3, not a huge lot to import because it's going to be very, very code light, and it's going to be very sort of concept dense. So don't worry too much. We're going to be very little Python. This is much more a chance for you to sort of look at this and get some of those concepts into your head first. Tuesday, Wednesday, and Thursday, Riley's going to come in. He's going to talk through 2 different libraries, Keras and TensorFlow. And that's going to be how we sort of start building these networks out actually in Python. So cool. Before I get started, if you got any questions, go ahead and throw them in the Slack, and we'll sort of talk through any of them that might be there. But I think we're good to get started. I know Chicago's going to kind of join us in a second, so they're just going to catch up that way. So cool. So I'm going to start running off my inputs. Math library, going to do a little bit of math, and then sort of plotting. And that's really kind of it for this. So neural networks, which are super exciting, right? They do a lot of really, really cool things. And before we sort of talk about what they are, let's talk about some of the ways that they've been applied. So for example, there's something known as the Deep Dream Generator. This is also off of Google. And this is a case which is not loading because there we go, latest dreams. Come on, there we go. So one thing that neural networks have been used for before is to take it's for image recognition, right? And so this involves sort of looking through smaller and smaller parts of that image to find something that makes sense. And this Deep Dream Generator uses those neural networks, which is technically trying to predict one thing, something using an image, and sort of helps transform it halfway through. So you get these sort of beautiful, combined dream-style sort of pictures. Where you can really take 2 different types of pictures and apply one style to one of those images, which is really cool. That's a pretty fascinating application of neural networks. Another one is this thing known as QuickDraw. And so QuickDraw is, again, Google sort of has like pioneered a lot of this different stuff that's happened. But this is a case where a neural network's going to look at what you're doodling and assign it or sort of say, this is what this looks like. Which is actually really fascinating. So here, I'm going to draw a screwdriver in under 20 seconds. And as I start drawing the screwdriver, so I'll kind of give it, and as you sort of draw, it'll actually sort of guess line by line what it thinks that you're doing. And we can kind of work through each of these images. I'll go ahead and throw this in the Slack. It's definitely sort of really fascinating to play around with. Let's see what else. You should have all probably already seen this, which is this is a DeepMind or a deep network known as AlphaGo. It beat the first human professional Go player on a 19 by 19 size board. Basically, it's sort of a really, really fascinating application of neural networks to play this board game known as Go. It's a very old sort of strategy board game. Go is a really interesting application of sort of predictive modeling because as you, essentially the space of all the different ways that you can apply or that you can make that next move is very, very large. And so that kind of puts you into a position where our sort of typical rule-based AI, so what we used to do for, say, creating things that played chess or played Go is that we'd create rules. If the human player does X or Y, do Z. If the human player does A or B, do C. Well, what the problem with Go is that, let's just take a look at the board real quick. So Go, or Ego, looks kind of like this. And essentially, you start by placing black or white tiles on a grid of up to 19 by 19 points. This means that your first few moves have sort of an astronomically huge number of places that they can be. Chess starts off very simply. There's only so many pieces you can move at the start, and that sort of space of that next move is very limited. Rule-based stuff tends to fail pretty spectacularly, though. What they did is they trained a neural network, and after a lot of layers and a lot of training, it was able to sort of pick out the best move to do next, and finally was able to beat an actual real human player. This is the sort of thing that when it happened, leading researchers were saying that we were 10 or 15 years away from that happening. So it kind of tells you that like this sort of science is very cutting edge and very moving forward quickly. So neural networks are incredibly predictive. They do things incredibly well and incredibly with a huge amount of strength. But we'll sort of talk about why they work and how they work and sort of all the different things that kind of go into building that model out. But it is sort of more of the cutting edge of predictions. They do very, very, very accurate predictions at the cost of almost no interpretability and a very long training time. So what are they? So neural networks basically try to train a set of weights that when together, you give it a set of inputs and it gives you a really accurate prediction for an output. And just like a lot of our past models, we're going to use that sort of loss function. So that loss function is going to tell us for all of our predictions, how far off are they from those actual values? And over a set of iterations, our model, our neural network, is going to try to minimize that value. The way neural networks do this is that they sort of establish sets of neurons, and these are known as hidden layers. They take in some sort of input, they apply a weight, and they pass that output onward. And as we sort of do this, as it sort of seems that data over and over and over again, it's going to change those weights based on how that loss function changes, until we see a really, really specific set of predictive weights. So one thing to sort of like immediately sort of hit the brakes and talk about is we're always going to want to know this question, right? Why does one neuron turn out like this and the other neuron goes a different way? We're not really going to be able to understand that. This is very, very, like this is just very basically mathematic optimization. There is no sort of effect of something or some sort of interpretable value that we're going to get out of this network. We're just going to get a really, really precise, mathematically optimized set of values. Deep dreams sort of, this is what we talked about before, deep dreams sort of kind of came out of this, this idea of can we see what the neural network's doing halfway through or part of the way through? And so if you look at stuff, let's see. Let's see if I can't find what I know is out there. Oh, nope, that's just going to be actual neural networks. Not super important, but basically it was an attempt to kind of see what are the things that the neural network is looking for at a specific part of that image recognition. That was the sort of basis of where Deep Dream sort of came out of. And you'll sort of see neural networks described kind of like this, where we have some set of inputs, something that happens in the middle, which we'll talk about in a second, and then something that changes all those inputs into an output. And as we kind of iteratively feed data through this network, we'll come back in here, we'll tweak these weights, and change them over and over again until we get like the best possible ones. And that's it. It's just basically, we're sort of using brute force power on our computers to sort of say, what is the best possible thing to output here? We're going to talk about some of the theory behind neural networks. We're going to talk about the topology, or what's known as the shape of it. So how many layers, how many neurons, what feeds into what, and in what order. And we'll talk about how we fit those weights. And then we'll sort of, oh, that's an older part before we did that. We are not going to sort of write out a small neural network in Python. That was before we had scheduled this AMA. You all will get lots of practice coding neural networks up tomorrow, Wednesday, and Thursday, using libraries like Keras and TensorFlow. So there's a lot of different moving parts. And what we're going to do is we're going to sort of try out these different things. We're going to try out different values using this playground.tensorflow sort of thing. And this will sort of take us through kind of the basic, easiest way to do this. So you can kind of imagine, this website usually takes a little bit of like sort of investigation or walkthrough. So make sure you do have it open up in your web browser. You can kind of imagine what we're doing here is that we have an x1 and an x2, so two different variables, and we have some sort of transformation of each of them. So x1 squared, x2 squared, x1 times x2, sine of x1, sine of x2. And we're going to use those with some sort of different set of hidden layers and a bunch of other things to try to predict either are things blue or orange, or we could possibly change this into a regression problem. That's sort of our setup for this playground.tensorflow website, which we'll sort of tick back and forth between to sort of practice these concepts that we're learning. OK, so hopping back. So let's talk about what goes into this network. So much like all of our other machine learning techniques, we are going to have to feed data into this network. And so for smaller examples, you may not need to worry too much about like how that data looks like. But typically, we're going to normalize it to be between 0 and 1 or -1 and 1. And this is because we kind of want to make as little work for the network as possible and sort of creating small tweaks up and down of a few decimal points up and down versus having to jump 10 points this way and 100 points that way based on that scale is more difficult. So what we'll do is we'll sort of normalize or standardize that data going into it. I typically normalize it between 0 and 1, but standardization would probably work just as well. And this is going to help the network sort of find a solution faster than it would otherwise. But outside of that, you can treat the features going into there almost exactly the same way as you would other cases. So if you were thinking about how we might put things into a random forest, same sort of concept. And much like our other supervised machine learning techniques, we're going to need an output at the end as well. There are ways to use neural networks to do sort of unstructured technique. What we're going to really focus on for this part of the course is structured machine learning, structured neural networks. For regression style, usually just one output is fine. If we have a classification technique, typically an output per class is a good idea. So if you have a 0 and 1, one node is fine. If you have a 0, 1, or 2, 2 nodes or 3 nodes is good. We'll sort of, you'll see cases of this tomorrow and the next day. So cool, right? If we take a peek back over here at that TensorFlow website, if we get rid of all those hidden layers, we have exactly that. A couple of inputs, x1 and x2, and an output, which is going to be what that sort of associated part is. Is it a 0 or is it a 1? So cool, right? So far, so good. We're looking exactly like we did with all of our other sort of machine learning techniques. We take some inputs, we might standardize them or normalize them first, and we'll do something in the middle and get an output. And we're going to compare that output to what our actual values are. So here are the new concepts. Here's what's sort of new in neural networks. So neural network, at its core, is built up of what are known as neurons. And these neurons take in some set of inputs. These can either be those original ones like this, or what's come out of another layer. It applies a weight to each of those inputs. It sums them all up, and then it feeds them through something known as an activation function. So it kind of looks like this. And what we'll sort of see is that it's kind of composed of two different things. A bias term, which is sort of like a constant or a beta 0 if this were a linear regression, and the input terms they've received multiplied by a weight. So I'm going to switch over to my whiteboard real quick. So I'm going to try to do both have like an actual real image and then also draw things out as well. What we might imagine is, imagine you had a linear regression, right? And you have some features over here, feature x1, feature x2, feature x3. What a linear regression does is it says, OK, cool. Take some constant over here. Here's my bias term. And then sum up each of some set of weights. So 1 times x1, weight 2, x2, and so on. And these two things together should output to a y-hat, right? If we imagine this being sort of our, if we took this and pretended this was a linear regression, this is exactly what we would do there, right? We'd take a constant, we'd sum up whatever that coefficient times x1 is, then the coefficient for x2 times x2, coefficient for x3 times x3, all the way through down to the end. And so what you'll see within these sorts of neural networks is exactly that, right? And here's the sort of neural network version of that. We have some sort of inputs again, x1, x2, x3. These will all go into some sort of neuron. Inside of that neuron, it's going to be bias plus the sum of the weights on it. That's all that's going to happen in here. And then over here is going to be our y hat. And this is sort of the simplest way to think about what is happening in a specific neuron. Where a neural network gets really cool is that we're going to do this multiple times. But you can imagine this in its very simplest case is exactly like that. And what you should sort of come away with is this looks like, in its simplest form, just like multiple linear regression, right? Where neural networks get really cool is that it's how we fit it and how many times we do this that sort of makes neural networks really interesting. But this is, at its core, very, very akin to that. And we'll see sort of cases where that gets applied even more specifically. So again, take in some inputs. This is what a neuron is. Take in some inputs, add a bias term, sum everything up, and then we'll sort of put it through this thing called an activation function, which we'll talk about in a second. And so that's really cool, right? That's very that's sort of a very new way of thinking about a neural network, but it should take you back to a case that we've already covered many, many weeks ago. So Kevin in New York is asking, are the weights overriding our beta coefficients? Yes. So Kevin's asking, are the weights trial and error, or are they derived from our coefficients in linear regression? Much, much more closer to trial and error. The concepts are very similar, where we're going to use how well we did with our loss function, and we're going to try to minimize that to get a specific set of weights. But instead of doing it just once and getting that full set of that best fit line, we're going to do it multiple times over and over and over again until the weights sort of fall into the right position to get us the best value. But yes, you can kind of imagine it as if as we pass data through, we're overriding what those beta coefficients are. It's not quite right to call them beta coefficients in this case for the neural network, but they're in the case of just one node, they're akin to it. Cool, awesome. And yeah, if you have any other questions, everyone, please just go ahead and throw them in the Slack. We'll sort of answer them as we keep moving. So that's a neuron, right? A neural network is basically made up of these neurons. So that means that we're going to have multiple of these cases where some inputs are coming in, we're applying some sort of transformation to them, and we're sending that output forward. And where this happens is something called the hidden layer. And the hidden layer is not devious. It's not secretive. It's not bad. It's just a layer in the middle of the network that's not the input layer or the output layer. And this hidden layer can have any number of neurons in it, and there can be any number of those hidden layers in your model. Notice the asterisks over here. There are more considerations than just what we feel like looks best. But for right now, we're going to skip over that. So at each layer, every neuron in that layer sort of gets the same weight. And we're going to start off basically with a random set of weights. And based on sort of what those weights and those biases are in there, each of these hidden layers is going to transform that data in a specific pattern. So if we hop back over here to playground.tensorflow, right now we've got no hidden layers. So basically these weights kind of come in, they get transformed, and out that comes. But as we add in hidden layers and hidden layers and hidden layers, now we have multiple cases of these weights being applied to different inputs, to different outputs. That's sort of the magic of what this neural network is. So in this network above, right, we've got these two hidden layers over here. Let me zoom out for a second. We have these two hidden layers, an output layer and an input layer. So in hidden layer number one, let me go ahead and grab my annotator real quick. So you can kind of imagine for hidden layer number one, that's going to be this one right here. We've got 4 neurons. Each of these neurons is going to take in 6 inputs. And it's going to, for each of the 6 inputs, assign a weight to it, multiply each of those inputs by their corresponding weight, sum them up, add in a bias term. Then we have this second hidden layer here. And this second hidden layer has 3 neurons. And each of those neurons is going to take in an input from the output of each of these models. So the weights inside of this neuron over here on the top here is going to be different than the one down here, even though they see the same weights. The input for this neuron over here is going to be the output of neuron 1, neuron 2, neuron 3, neuron 4 in that first hidden layer. So here the number of inputs is 4. But otherwise, same sort of concept, right? It's going to take in some inputs. It's going to apply a weight to each of them. It's going to multiply the corresponding weight by the corresponding input. It's going to sum them up. It's going to add in a bias term. And it's going to pass that outwards. Then we sort of come to this output layer, which is sort of the way that we take all this work and combine it down or distill it down into one number. And this is going to be one more case of a neuron. It's going to take in 3 weights, which are the outputs of each of these 3 neurons, which are the outputs of these 4 neurons, which takes in these 6 inputs. And it's going to come out with just one value at the end, and that's going to be what our y hat for a given case ends up looking like. Now again, we're not talking about how we assign these weights. We're just going to assume at this point that these weights are good. So that's sort of where we're at, right? We've got this really dense network of a bunch of neurons working together, either on that same, either on those input weights or on the output of previous neurons. So cool. So let's take a couple minutes. We'll take 3 minutes. This should be pretty quick. Partner up. Here's a sort of like example neural network. This is essentially something about so churning over here on this right-hand side. That's what we're trying to predict. A churn is whether or not a customer leaves your service or not. And this sort of fake neural network, this sort of example neural network, created something, right? They have a bunch of inputs on this side, some number of hidden layers with neurons, and an idea of whether they are a churner or not a churner. So together, like with partners or whatnot, how many layers are here? Which ones are inputs? Which ones are outputs? Which ones are hidden layers? How many neurons exist in each of them? And then try to like really look at these hidden and output layers and say, OK, what's going into each neuron? What's happening inside of each neuron? And then what is it outputting at the end? So we'll take 3 minutes. It should just be kind of a run through of what we're seeing. And we'll sort of come back after that. Okay, cool. So yeah, so let's take a second. I'll walk through like how I would see this sort of problem. So in this case, right, we've got 3 layers in this network. We've got our input layers over here. We've got one hidden layer of 6 neurons, and then our outputs, which are going to be essentially transformed into likelihoods of being a non-churner or a churner. In our sort of input layer, we've got 8. Is that 10? That's 10. 10 different inputs. So these are different things about sort of phone things in what I'm assuming is France. So international fees, SMS fees, whether or not it's got 3G, that sort of stuff. The hidden layer here, the one hidden layer we have, has 6 neurons. Each of those neurons takes in all 10 inputs. It sums up all of them. It multiplies each of them by their corresponding weight, and it adds in a bias term. So what's coming into here is all 10 of those features into each neuron. Each neuron's outputting 1 number. And then our sort of output layer over here is taking in each of these 6 inputs, again, summing up and multiplying them each by their corresponding weight, summing them all up, adding a bias term, and passing out some value for churner or not churner. So that's kind of like what, we might look at this and say, like, this is the topography of this network, right? 1 hidden layer, 6 neurons, 10 inputs, 1 output for each class. OK, I see a few people typing, which is good. Let me pause here and let those questions come out. I see what you mean. So Josh and Benny have both sort of pointed out that in this case, it looks like something like AV local SMS or AV international fees are only feeding into certain neurons generally. Yes. So typically it's going to feed into all the neurons at once. So I'm going to assume that this is probably not necessarily saying specifically it only feeds into those 3, but that it's just drawing to make that a little clearer. There are ways to sort of have them feed into only a set of different neurons. We're not going to worry too much about that right now. But yeah, so typically this would feed into all of them at once. Hong in New York is asking, do you choose the number of neurons per layer? You do. We'll sort of talk about what a good neural network looks like, or how to sort of go about picking that topography a little bit later on today. Halina Austin is asking, if you have more than 1 hidden layer, does the number of neurons always stay the same or decrease, but never increase as you progress through? Again, that's going to be the sort of thing where that is up to the modelers to decide. Typically, it'll stay the same or decrease. It won't typically increase in the middle and then come back down again. But there's nothing technically stopping you from doing that. Again, that's going to be sort of just like hyperparameters in a model. It's going to be something we sort of choose as modelers and tweak or iterate as we process that data to find the sort of best topography of that network. Ajanthan Boston is asking, how do you determine the optimum number of neurons to use in a real-life scenario? Does it depend on the features that are being fed into the model? That's a great question. And we'll sort of cover that a little bit later on down the line. But again, that's going to be sort of very, very modeler dependent. And it's going to be dependent on your data. It's going to be dependent on a few different limitations in the network. And it'll be dependent on how long you have to fit or train these models. Chris is asking, are all neural networks based on Bayesian stats? I can't imagine otherwise. So it's not necessarily Bayesian stats, right? What we're really doing here is we're sort of, we'll sort of talk about how that gets fit later on down the line. But what we're doing is we're really sort of like mathematically optimizing what these weights should be. So it's less about Bayes and more sort of about calculus and gradient descent, which we'll sort of see later on down in there. So Andrew has a really good question out of Austin. If you have multiple output nodes, what is the interpretation of the results from each one? So typically, we'll have multiple outputs for classification cases, right? And what we'll typically do is we'll sort of talk about activation layers in a second. But there's something we'll do at the end to each of these outputs, which will say, OK, what is the likelihood over here that y equals 0, 0 to 1, right? And then down here, we'll apply some sort of transformation to the output to give us that likelihood of y being equal to 1. So if you kind of imagine, if you've ever done sort of predict_proba for your logistic regression, your random forest classifier, that sort of stuff, and it's come out with the likelihood that some row is predicted to be class 1 or class 0 or class 2, and those sort of likelihoods sum up to 1. That's sort of what this is doing, is we're asking our neural network to predict how likely is it that row number 1 is a non-churner, how likely is it that row number 1 is a churner. And that's sort of what this output node is doing. This is basically saying which one of these is most likely or least likely. If we wanted to just say which one is this a churner or a non-churner, we just go ahead and pick whatever the maximum value. So if the likelihood over here that they're a churner is higher, or the highest out of all the possibilities, we'll just say, cool, our network says this row is churner. That's what we predict. But that's sort of what we're, under the hood was what's happening there. All right, cool. Awesome. Let's keep walking down. So yeah, so this is going to be sort of, we're just going to, I really like these questions. That means that sort of the understanding that we're getting here is good, and we can kind of keep moving forward to the next step down the line. So neurons have what are known as activation functions. And what activation functions do is it's sort of this extra step in this process. So if you remember, I'm going to go back and sort of share my screen here again, my whiteboard. If you remember back when we had this sort of basic thing, there's one other extra step that we haven't really talked about, which is what happens here, right? And this is what's known as an activation function. And it's going to be a thing that we feed all of that value, that final value into and transform it in some way for the next step. So there's a couple different ways to think about this, right? If we had sort of x1, x2, and x3 again, and we fed them all into one neuron, and we want to output y hat, one thing we could do is we could apply an activation function that transforms it in such a way that that actually nothing happens here, right? So one thing to do here, let's imagine that this gets assigned to something called z. So we put this in here. Our output at this point is known as z. An activation function is going to be some sort of codified transformation we apply to all of the outputs of these networks first. So there's a couple different ways to do it, right? The easiest one is this thing known as the identity function. So we're going to say, for this output z in this node, what I'm going to do is I'm just going to return out or pass out that value. So this is going to be z. So if z is equal to 2, that's really gross. Let's sort of make that a little clearer. So if z is equal to 2, y hat will be equal to 2. If z is equal to minus 2, y hat will be equal to 2. And this might be like the sort of most common thing to do. And you can imagine us doing this for every single linear regression we've ever seen. Just take this and apply out that sort of value. But we've used activation functions before in the past. And what we've used it for are logistic regressions. So if you remember our sort of logistic regression, it looks sort of the same way as a regular linear regression does as well. We have some sort of sets of weights and some sort of inputs. So x1, x2, and x3 come into a network. We sort of sum up the bias plus the sum of all of these weights by their respective thing. And then we do something to that output, right? We do something to that output in the middle, known as phi, and that takes it and constrains that output to be between 0 and 1. Right? And so we apply some sort of transformation to this model over here that takes that output and squishes it between 0 and 1. This sort of graph might look pretty familiar to that, where we've got an output of 0 and an output of 1 here on the y-axis. And what we're looking to do is sort of create this sort of thing, where we're saying, you know, we've got some values over here. Those we're going to constrain to be very close to 0. We've got some values over on this side, which we'll constrain to be 1. We'll pass it through some sort of logistic function. That's an activation function. We're saying, great, here's my linear model. Here's my linear combination of terms. Take some weights, multiply them by those inputs, sum them all up, add a bias. And then I'm going to do something to that output to make sure that what we're outputting is a value between 0 and 1, no matter what the weights are or the inputs are over here. And so within a neural network, we're going to have a lot of different cases of this. So you can imagine having x1, x2, x3. We'll sort of do that bias. We'll sort of take the bias. We'll multiply them all the weights. We'll sum them up. And then what will happen in all of our networks is some sort of activation function, which will apply to the output of that neuron before it goes into that next one. And so we could have things like the identity function, where it's just going to pass out that same value twice. We could have something like a logistic function, where it's going to take that and it's going to constrain it between 0 and 1. This f of a over here is just saying, if I give you a, what am I doing to that? If I give you the output of here, what do we see over here for y hat? And it turns out there's a lot of different things that we can do for activation functions. We've already used them. We've already used them in logistic regressions to go through and say, here's a regular linear model, but constrain what comes out of here to be between 0 and 1. We're going to do that in a lot of different ways within neural networks. So cool. So Chris in Boston is asking, are you referring to the link function in generalized linear models when you say that it's the same thing as an activation function? Yeah, that's probably a good way to think about it. In that specific case of one neuron, inputs go in, one output goes out to be y hat, they're kind of analogous in terms of the conceptual understanding. Now, we're going to do a lot more than just one model with this, but that's sort of the same concept there. So we have a lot of different possible activation functions. And as you guys have questions, go ahead and put them in the Slack. I've got my eye on it. So one sort of thing that you'll see a lot of, and there are a lot of different functions we can put in here. Here's the activation functions page on Wikipedia, and here are a whole bunch of different cases that you might use different functions for. So there's a lot of them out there. Some of the common ones we might use are something known as ReLU, or the rectified linear unit. What all this does is it says if you're going to output some sort of negative value, just don't output anything. Turn that on to 0. So let's kind of imagine what that looks like, right? If you have, this is the same sort of idea of if some combination of weights and terms creates a negative value, we're just going to turn that neuron off in that case. And that ends up giving us some sort of output that looks like this, where we have some sort of x coming in and some sort of response of x. Anything below 0, it's going to turn out to be 0. So we're just saying this neuron basically doesn't do anything if its output comes less than 0. If it's greater than 0, we're just going to give it that usual sort of x part over here. So Kelvin is asking, so the key in neural networks is choosing your activation function. It's one of the keys. There's a lot of different sort of parameters that we can tweak with that, but definitely thinking through what that looks like is important. So let's see. Let me clear that off and switch back over here. So we might, so again, there's a couple different other ones, right? There's this thing called softmax, and softmax is going to do this sort of concept up here, where we say, take in a bunch of stuff and constrain this to be some sort of float between 0 and 1. It squishes a bunch of inputs, and it says, essentially, what the probability of falling into that specific class is. Also, we can use something like a sigmoid or a logistic activation function. And that's going to do the same sort of idea that our sort of logistic function has done before, where we take in a bunch of terms, we sum them all up, and we apply this activation function to say, we're going to squish you down to look like this. And so really, what each of our sort of inputs and outputs look like is this. You can kind of imagine this is the actual full interplay of one neuron. We take in some x's, we apply a weight to each of them, we sum them all up, then we pass that total through this activation function to create some sort of change in that. Ben is asking, what is the soft plus? I think you mean the soft max, which is sort of basically going to give us a probability. So cool. So let's try to think about, if we hop back over here to this TensorFlow playground, right? We can see that we've got a bunch of different activation functions to play with. So ReLU, which is going to say if it's less than 0, turn it to 0. If it's greater than 0, keep it at 1. tanh, which does that in a slightly different fashion, sigmoid, which creates that sort of logistic regression kind of snaky figure, and linear, which says, if you put this in, put that out. Okay, so Ben, okay, great. So Ben has kind of posted a picture in the Slack, which is the one we were talking about before, where we've rectified in Soft Plus. Soft Plus just basically is a slightly different transformation. It says if it's super negative, we want that to be 0. If it's just a little bit under 0, we kind of want it to have a smaller value. And then outside of that, we want it to have its sort of normal case. So it's just kind of saying, let's do rectified linear units, but with a slightly softer, curvier response around that 0 point. So cool. All right. So Anthony's asking, what is the basic difference between the softmax and the logistic activation function? That's a great question. And so that's kind of why I've thrown these Wikipedia articles in here. What softmax is going to do is it's going to do something. Essentially, it's going to kind of give you a generalized logistic function. So it's basically going to take something into it's going to do that for multiple outputs at the same time. So if we wanted to sort of create that sort of snake thing and put it across multiple outputs at once, as opposed to just 0 or 1, that's when we'd use softmax. Otherwise, we'd sort of use logistic, which will take it all and just put it out between 0 and 1. So softmax might happen much more likely at the end or the output. Logistic might happen in the middle of the network. So Kelvin asks, is it good to be versed in the common activation functions for neural networks? Yeah, there's these are a form of hyperparameter, right? We can try different ones and see which one works better for our specific case. Typically, there's a lot of different ones. Most of them are rarely used. Some of these are much more frequent. But yeah, taking a look through taking a look through that article, kind of seeing what those look like, can be really helpful. All right. Cool. So let's talk about picking your topology, or picking what goes into this network. So the number of neurons, the number of hidden layers, the type of activation function, those are all different things that we can sort of tweak to change how that network performs. And there's no really good hard and fast rule for picking what goes into there. There's going to be a combination of experience, research, exploration. All of them are going to help decide what that looks like. Sometimes there are different cases where there's a standard that exists in the research. So for things like image recognition, there's certain types of neural networks or certain inputs or certain layers that have been found in the past to work really well. So usually that's a good jumping off point. Or if you've worked with a set of data before, you might have this experience that says this is this is a good application for 3 layers, or this is a good application for 1 layer. If you have no good idea what to do next, one good place to start off with is an input layer, one hidden layer that has the same number of neurons as you have inputs, and then an output layer with that appropriate function. So if we're going to hop back over to our sort of TensorFlow playground, that might look something like this, where we say, OK, taking the next one and the next 2, we'll pass it through this hidden layer where we combine those terms, apply a bias and an activation function, and then our output layer will combine those 2 outputs and give us a prediction of 0 or 1. That's a good place to start off with, but you can add different layers or different nodes as we sort of move forward. So now, what we sort of talked about here is the difference between a single layer and a multi-layer perceptron. And these are just different types of neural networks. A single layer perceptron doesn't have any hidden layers. It's just the inputs combined up to be an output. So this would be an example of, there we go. This would be an example of a single layer perceptron. Inputs come in, we combine them, we apply an activation function, and we get some sort of output. Once we get above that, that's going to be any sort of multi-layer perceptron. So this, our sort of like default kind of case, is going to be our multi-layer perceptron, where there's going to be at least 1 layer between that input and that output. So Kevin in New York City is asking, is it good practice to use activation functions on each of your hidden layers, or only on the last layer before the outputs? So what we're going to do is we're going to apply the same activation function to all of the neurons in a given hidden layer. And we're always going to have some sort of activation function. Now, sometimes that activation function will just be as simple as whatever's coming out of that neuron, pass it directly into the next layer. Sometimes it'll be more complicated, and we'll do the sort of logistic thing to push it back between 0 and 1. But we're going to apply the same activation function to all of the neurons in a given layer. We're definitely going to do it on that last layer as well before those outputs. And this can be really helpful, right? If we think through, if we imagine our sets of weights, and let me hop back over to my whiteboard real quick. If we imagine, right, that we have some sort of larger layer. So I've got my inputs over here. They all kind of go into, say, 2 different nodes. And let's say I do this twice. So I have 2 hidden layers. What I might want, right, is the weights inside of this neuron are going to be some sets of 1 down to 4. The weights in here are going to be some set of weights 1 and weight 2. And what I want is, as I fit this, for these weights for little motions in these weights to be as good as possible. And so I really want to see zeros and ones coming in through here, so some sort of normalized scale of data, zeros and ones coming through here. And I also want the nodes in this one to see stuff coming between 0 and 1. That's where these sort of activation functions might help. If these 4 things come into here, and my output on this side ends up being, say, 4, what I want to do is I want to pass it through that activation function and turn that back into some sort of value between 0 and 1 before it sees that next set of weights. And that way, us training the weights for this neuron and training the weights for this neuron can be a little bit easier, right? We don't have to think about weights that might see really, really large numbers or really, really small numbers. And that's sort of where we're going to make sure it's sort of our safety guard, to make sure that we're only seeing stuff that makes sense for each of those weights. So Hallie is asking, can you have different functions on different layers? Yes. So you may have softmax on your output layer and tanh or linear or ReLU or identity functions on some sort of inner layer. Yes, you can definitely do them across different layers. Within the same layer, we're going to have the same activation function, because we want all of those inputs for that next layer to be sort of the same scale or the same idea or the same shape. Okay, cool. So let's sort of get some hands-on work with these activation functions. What we'll do is we'll take a 15-minute break here. Part of that time will be working with a partner or independently, your choice. Pick at least 2 of these different sort of activation functions. So binary step, ReLU, logistic or sigmoid, tanh or soft sign. And each of these has that sort of mathematical equation. Go ahead and write a function for at least 2 of them in Python. And then what can be really helpful is pass in different values. See how that function changes the value 100, the value -100, the value 2, the value 0, from what it was to what comes out of there. So stuff like binary step, you should be able to sort of expect, well, if it's under 0, it'll be 0. If it's above 0, it'll be 1. But go ahead and try to write these out in Python, and then see how that changes over different values. And so we'll sort of take 15 minutes here. That'll include our break. So we'll come back at 10 a.m. Central, 11 a.m. Eastern, and we'll sort of talk about how we fit these models, how we change those weights, versus just how we set up the network to take them in. So let's get started with that. You can work with a partner. You can work independently. It's up to you. I would suggest working with a partner, but again, that's up to you. So cool. I will see you all back here in 15 minutes. Okay, cool. So hopefully you got some practice in trying out those activation functions. What I'm going to do real quick is just run through one of them. I'm going to run through this logistic or sigmoid function, and we'll kind of see what that looks like and what that does to a set of inputs. So I'm going to write this code out real quick here, and then I'm just going to throw it out in Slack. So you can imagine creating this function, right? All f of x is saying is, I take in an x, and this is what I do to it. So we'll take in some sort of x. And what we'll take back out is that x with 1 divided by 1 plus math.e. So this is, again, this is going to be the what's known as the natural logarithmic or Euler's number. This is a very, very long float. Don't put this in manually. Just rely on the built-in math library to do that for you. Raised to the power of -1 times whatever our x is. And so if I say, what is the sigmoid of 2.5? It's going to go through and it's going to constrain it to some value between 0 and 1. And in this case, it'll be 0.924, et cetera, et cetera. We might even do something like this where we plot it out to see what that looks like. So we'd have some x's, which will be, we'll say, between -25 and up to but not including 26. So it'll be -25 to 25. Some y's, which are going to be sigmoid x for x in x's. So for every value in our x's, let's go through and pass it into that sigmoid function. And then we could do plt.plot x's and y's. And that'll kind of show us what is going to happen for these different values of x as we pass it through that sigmoid function. And what you should see here is what that sigmoid function, that activation function, is going to do is, no matter what comes out of that neuron, it's going to constrain it to be almost 0 up to almost 1. So let me go ahead and throw that into the Slack for you all to chew on. But that's sort of what our activation functions are doing, is that it's saying, here's a great output from this neuron. Let's do something to it to make sure that it's easier for the next neuron to sort of process. Looking at the Slack, most people who did vote on how the material's going are around a 2 or a 3, which is good. Stuff's a little, it's definitely a little bit of a denser material, so kind of working through that is really helpful. And apparently most people had a pretty good Thanksgiving, which is awesome. One other person had literally the best human holiday ever, so good job. That's great. All downhill from here. So cool. Where's my mouse? There we go. So let's sort of talk about how we train this network, right? We've kind of to this point said, here's a bunch of neurons, here's a bunch of weights. We're not going to worry about how we get to those right weights. Here's sort of how that fitting process works. You could imagine that a neural network could have really, really bad weights, right? That, take in input x, multiply it by 10 million, take in input y, multiply it by -20,000. And here are some weights that would give us really, really wrong answers. We don't want that. We want weights that give us good answers. And so what's going to happen is that it's going to be a sort of combination of 3 different concepts. We have some sort of loss function that's going to help us optimize the values that we are looking for. We're going to talk about what forward and backward propagation do. And then we're going to talk about what gradient descent is, which we've sort of covered before, and how that changes those weights. So cool. So loss functions, we've seen these a lot before. And they're functions that take in the actual values for our certain rows and the predictions that our model puts out and gives us a value that we want to minimize or sort of shrink. You might also see these called cost functions. So within regression, you might have seen sum of squared errors. We take the actual output, we minus the prediction, we square that value, we sum them all up. Bigger values mean that we're, on average, worse off. Or mean accuracy for classification. How many things do we classify correctly over how many different rows do we have? Again, we're going to take all these predictions and actual values, sum them all up in some sort of, or aggregate them in some sort of function, and that value, as it goes up or down, is going to be better or worse. So what we do with our neural network is we use something known as forward and backward propagation to tweak the weights. And this is going to be an iterative process. We're going to send that data through over and over and over again, feed it forward through the network, and then we're going to feed our errors backwards. And we'll do this over and over and over again until we sort of have said, this is the best that our model might do. So forward propagation is pretty straightforward. Take some data, pass it into this network, apply the weights, sum them up, apply the activation function, pass it all the way through, and at the end of that network, you'll get some sort of predicted model or predicted value, which will look something like this. I sort of put this up together before the while we were on the break. So here's a network. Forward propagation is basically going to go through, and it's going to say, okay, for every set of x's I have, go and apply all the stuff in layer 1, go and apply all the stuff in layer 2, go and apply all the stuff in layer 3, and get me some predicted output for that set of inputs. And if you think about this, right, we have 5 weights to train in each of these neurons, 1 bias term and 4 weights. We have 12 weights to train in this network, right, in this layer, because we've got 3 inputs and 1 bias term for each of these. And we have 8 weights over here, 3 weights for each neuron, and 2 for each of those biases. And so what we want to do is we want to go through and kind of pick out what we want to do, right? This is going to be how we train these weights. So the next step is, through this pass, we've gotten through here and we've gotten to this y-hat. What we want to do with backpropagation is see where we're at and how far we are away from the truth using that loss function. So are we really, really far off, or are we very close to where we're supposed to be? Then we want to look back in our network and see which neurons kind of led us in the wrong direction the most of the way. And then we want to tweak all of the weights to make that model more accurate. So basically, we're going to look at how far we are off from our predictions, work backwards or propagate those errors back, change the weights based on how bad each neuron did, and then send the data through again. And what we'll do for fitting this network is we'll pass that data in a number of sort of full passes known as epochs. So some epochs might, you might get that done in 100 or 200 or 1,000. Sometimes there might be many, many more epochs. This is a thing that you might hear a lot in sort of data science interviews, that sort of thing, is this idea of the curse of dimensionality. And you might say, well, why don't we just try all the different weights, and then we'll find whichever one is the exactly best one. Well, this is the curse of dimensionality, is that we have so many different weights to try, and so many different unique combinations of those weights going in different directions that it's impractical to try all of them. If we have lots of weights and lots of interactions, so the weight 1 in the neuron layer 1 go in a different direction than some other weights, to try all of those different combinations can kind of take us past the heat death of the universe, right? There's so many different things to try if we tried them exhaustively. So what we're going to do is we're going to estimate what those weights should be instead. And we're going to use gradient descent to do that. And what gradient descent is going to do is it's going to try to find the lowest point or the smallest point of a function. And to do that, it's going to use what's known as the derivative, which tells us how far a function changes, either up or down, at a very small place around that. And so what we'll do is we'll look at our loss function for a certain point. We'll say, OK, if we change this weight this way or that way, do we go up or do we go down? And we'll sort of use that to guess where we should go next. So the learning rate is going to be how big of a change we make every pass. And the epoch is going to be how many times we fit that. Gradient descent looks sort of like this, where we say, if you kind of imagine some sort of function that we have, we're going to try to, each like sort of individual bit, the derivative is going to be this sort of tangent line to it. If we go up this way across some sort of weight, that should lead us upwards. If we go down, that'll lead us towards a lower point. We want to go that direction. And so you can kind of imagine it like this, right? This is the sort of magic that makes this work. When my whiteboard loads up, there we go. Our loss functions are the thing that we're trying to optimize, right? So our loss function is going to be some function of the weights we see. And so what we want to do is we don't know what that like actual sort of function actually looks like, but what we'll pretend is, or what we'll look at is, here's some sort of here's the value of that loss function. So in some cases it goes up, in some cases it goes down. And what we'll do over here is we'll try different values for weights. Now here we're just saying here's one weight that's changing it, not multiple weights. But you can imagine that our loss function might look kind of like this. And at certain values of weights, that loss function outputs a really high number, so like over here. And at some points, it outputs a very low number over here. What our sort of case of gradient descent is going to do is that it's going to look at different points and say, OK, am I going, at this point, if I increase my weight, does my value go up? If I decrease my weight, does my value for that loss function go down? The learning rate is going to say how far do we jump over to the next point. And so this is how we're going to kind of go through and figure out all the different weights for this network. Now, this is a very simple case where we have just one weight. And if you remember what we did before, and we sort of like walked through here, we have some 50 or 60 weights to sort of change all at the same time. And that's a little bit more of a task than just trying to find one. So what we end up doing here is we end up doing something called partial derivatives. We don't really go too far into that, but essentially we'll say if we change just one of these weights, what happens to the loss function, assuming that all the other weights stay constant, and then we'll sort of add up all those changes and do it that way. It's a little bit more complicated than that. We don't have a lot of time to go fully into the math, but what we'll do here is we'll basically look at how badly we did, we'll take those errors back up, we'll change those weights to sort of say, you were really wrong here, so change your weights in the opposite direction. And then we'll sort of kind of keep passing that data back in, forward and backwards until we see what we want. This is sort of an image I found online, which is pretty nice. One thing to note here is that our inputs are on this side, and our outputs are over here. So they've kind of flipped it around to look differently. So just as you read that, you're going to kind of read it from right to left. But this goes into a little bit more detail about the math behind how we sort of propagate those errors backwards. And this part down here helps a lot. That video, that YouTube series that I keep linking, is also a really good use case. They sort of explain the math a little bit in a little bit more detail. One other thing to think about with neural networks is this idea of what's known as the vanishing gradient. And this is a thing. This is like one of our sort of the things about neural networks that kind of keep us from making 15,000 different layers at once. Is that layers that are sort of very close to the input layer tend to train or tend to change at a much slower rate than the ones that are closer to the output. So sort of how much each neuron sort of adds or how much it can change vanishes as we go deeper into the network. So if we have a really, really deep network, lots of different hidden layers and lots of input nodes, it can take much longer to train that network without seeing a lot of a big boost. So we want to add like lots of layers in sort of carefully. Okay, cool. Let's tackle overfitting, and then we'll sort of take our break and then kind of get started with our AMA. So do we overfit with neural networks? And the answer is yes. Yes, we do. Cool. There's some stuff in the chat. Awesome. So do neural networks overfit? They do. If you imagine this is a fact of mathematical optimization, at a certain point, we're going to find the best way to predict that training data and not that test data. So there's two techniques we use to sort of ward off this overfitting part. And they are regularization and dropout. So again, just like we did with linear regressions and logistic regressions, we can talk about regularization. And what this is going to do here is we're going to say, let's make that loss function a function of those weights as well. So if you remember sort of our original sort of sum of squared errors, we have some sort of sum here. We take off that predicted value, we square those results. If the predicted value is really far away from our actual value, that drives the sum of squared errors up. And you can imagine some of our regularization or some of our regularized loss functions does that same thing, but it also adds in some sort of sum of all of the weights. And that might either be the weight squared or the sum of those weights in their absolute values. And what this is saying is, if we have lots and lots of big weights or lots of weights that aren't just zero, they better be really, really helpful and sort of do more work to reduce this value to warrant their inclusion. So this way we can kind of say, like, we're just going to include like the most important weights. So this is sort of the regularization that we've already talked about before, just applied to all of the weights in all of those different layers, not just one or two. The other idea is this idea of dropout, which is, I'm not quite sure what's happening in our Slack right now, but that's cool. So it's the idea, this other idea of dropout. And we can also use dropout to tackle this overfitting. And what this will do is for each pass, it's going to take some of these different neurons and it's going to say, actually, whatever you did output, just output 0 instead. And it's going to randomly choose some percentage of these neurons to remove during the fitting process. And what this sort of does is it pushes you to, it pushes each of your nodes over here to say, OK, I can't rely on always getting an input from some node behind me. The weights I apply here have to be applicable to a lot of different cases. It sort of forces, your weights to be more general. So again, just like everything else, just like all of the other sort of machine learning techniques that we talked about, neural networks can also overfit. We can use regularization or dropout to get rid of that. So cool. So what we'll do here is we'll take a 10-minute break. During your break, I'd like you to play around with this TensorFlow playground. You can add in different hidden layers. You can add in different activation functions. You can change this learning rate. So do we make big steps during this fitting process or lower or smaller steps? Do we regularize? And if we do, how much do we regularize? And what I'd like you to do is, like, at some point during this sort of 10-minute break, play around with this stuff. Once you hit this play button up here at the top, it's going to run them through different epochs. And you'll be able to see how that loss function changes over time. Now, in this case, feeding in x1 and x2 with 2 neurons in one hidden layer doesn't seem to be adding very much to that. But go ahead and try those things out. Kelvin asks, which is best, regularization or dropout? That's sort of a case where we don't know yet. That's, again, a sort of hyperparameter that you can try and see for your specific case whether that works or not. So let me go ahead and give you all that 10 minutes. What we'll do is we'll come back promptly at 10:35 Eastern, or 10:35 Central, 11:35 Eastern, and we'll sort of get started with our AMA. So I'm going to sort of tick off for a second and then sort of stop this recording and start a new one. But come back in 10 minutes. At some point during your break, try out that TensorFlow playground. And if you have any other questions about neural networks, go ahead and throw them in the Slack, and we'll sort of answer them in line. Outside of that, get ready for our AMA in about 10 minutes. We're going to go straight through from that point on to lunch. So if you need to go and take a break, do it now. All right, cool. See you all in 10 minutes.